unit on a odd topic, but sounds odd until you really think about it, and then it makes perfect sense, on gravitational potential energy in general. I was sort of working through some of the calculations before I did the video, and I was frustrated over something I was getting wrong, which you're going to get the same thing when you do your assignment. Uh, and I go, this isn't rocket science to Mr. Estall. Then I thought, well, kind of it's rocket science, but it's not brain surgery. So this is definitely not brain surgery, but it is a bit of rocket science. Calculations in outer space. And if you're thinking, oh, if Miss Stone was frustrated, then it was I was miscalculating scientific notation, and there's a lot of scientific notation in this one. So I was reading a large number, and I was assigning the wrong exponent, which is giving me all wrong answers. And I guarantee this will happen to you too. So be prepared to be frustrated with that sort of thing in the next few days as you work through problem set number 7. Anyway, so it's not brain surgery. It's a little bit of rocket science, though. Here we go. Gravitational potential energy. Well, we learned this. We learned that gravitational potential energy is mgh. The problem with this is, that's all well and good when you're on the surface of the Earth and g is equal to 9.8. What happens when you're out here? And what if you're out here? And we're talking about an mgh relative, say we're saying, usually we say h is relative to some other, like the lowest point in your problem is how we've always done it, right? Well, what if I'm saying right here and it's relative to the surface of the Earth? Well, you might say, okay, well, use 9.8, but I can't because out here g is not 9.8. In fact, g is going to constantly change as I go from the surface of the Earth way up here. Remember, when we use 9.8, we're using it as a very safe approximation because it does change as you lift up from the surface of the Earth. So theoretically, at the top of the Leviathan, it's a little bit lower than it is at the bottom. It's just that the difference is so small, on a roller coaster or anywhere near the surface of the Earth, that it's a very safe approximation. When we're talking about outer space, we can't do that. So I guess it's just important to have a good handle on that concept. You'll struggle through the calculations, and it's not that big a deal because they're not a big part of first year physics or anything like that, but at least understanding that you can't just, EG is okay, MGH at the surface of the Earth, but it's not really always true. Okay, so moving on. We've done this before, so this first little bit's just stuff you've done before. Use the term gravitational field strength. And of course, later on, when we talk about electric fields, we'll talk about electric field strength, but now we're talking about gravitational. And we give it the symbol G, and it tells us how much force 1 kilogram would experience at a given location. And we've derived this formula. We've done all this before. It's grade 11 physics. All review, okay? So, you take any object of mass m. That object could be, your coffee cup. It could be your pet pug. It could be anything. And you say, well, its force of gravity, mass times the gravitational field strength, or 9.8 in our case, is equal to the general form of gravity between that object and the center of the Earth. Well, if you said that, then you said, well, the mass shows up on both sides, I can cancel it, and here's our formula for gravitational field strength, okay? And you'll remember G. This stuff you should all remember. If you want to take a look over this more detail, just pause. But let's do a couple related problems. First of all, you'll notice here on the right that I screwed this up. Determine the gravitational field strength experienced by the satellite. This particular satellite, we're told the field strength. I just screwed up the question. It should be how far above the surface. So you might want to fix that up, and then we'll look at this first problem here. 277 refers to one of the textbooks that I refer to for the course. And if you find you're getting confused in this material, I'd rather you not take it home, but you can definitely look through the textbooks. I just don't want you to take it home because I don't want to lose track of them all. So, first question, we've got the satellite. It's got a mass of 225 kilograms, and it's orbiting that far, 8.6 times 10 to the 6 meters above the surface of the Earth. And we want to find, first of all, find the force of gravity between it and the Earth, and find the field constant at that elevation. Okay, so looking at this side first, you can sort of leave this for now. Here's the solution. Here's the information we have. The R is going to be how far above the surface of the Earth plus the radius of the Earth. So this is the radius of the Earth right here. Okay, so the R is always right to the center. So there's our R value. There's the mass of the Earth. Okay, so looking for Fg, you just substitute in the two masses, the R for where this object is, and you get 399 newtons. To get the field constant, there's two things you could do, is just use this equation here, because that is the equation based on what I showed you earlier, or you could actually just take this number and divide it by 225, because that's the number of newtons. This Fg is the number of newtons that 225 kilograms would experience. So therefore 1.8 newtons would be the amount that 1 kilogram would experience. And I'm going to put a check mark particularly on this one. This one, hard to say. We're dealing with crazy numbers in this unit, so it is really hard to know if you get a good answer. But this one I know it makes sense, because we know it's 9.8 at the surface of the Earth, and the further you get away from the surface of the Earth, it's going to get smaller. So it makes sense that it's something smaller than 9.8, and it can't really be negative. So that's a good answer. Okay, so pause if you need to keep writing, but I'm going to skip back to the question so we can look at this question. In this question here, we're given a 620 kilogram satellite, and we know the field strength is 4.5. And we want to first find out how far above the surface of the Earth. Okay, it's orbiting. So just jumping to that, we'll look at force of gravity afterwards. Really, this formula here, the G formula, I've taken it to isolate R. Right, so if you think about it, multiply both sides by R squared, divide both sides by G, take the square root. I'll leave you to figure out why that's true, but it is. And we solve it, and we know that then that gives us an R of 9.4 times 10 to the 6. But that's not the surface of the Earth, right? That's how far from the center of the Earth. So to get the height above the surface, you have to subtract the radius of the Earth, and this is the radius of the Earth right here. Okay? So just jumping, let's see, does this number make sense? Well, one thing I know, if the 4.5 is, it's greater than the greater than the G we found here, 1.8. That means that it must be closer to Earth's surface, somewhere between the surface of the Earth and this radius right here, 8.6 times 10 to the 6, above the surface. Let's just see. Yep, 3 times 10 to the 6. So it's quite a bit closer to get a bigger G value, which makes sense. Okay? And then force of gravity, then once you know the G for that particular location, you can find the force just by multiplying it, the mass of the object, which is a 620 kilogram object, the satellite there, and we know the G. So actually this is really easy. This is just a straight multiply. So even though you're not on the surface of the Earth anymore, you can just do that. So I'm going to check mark this one. We checked that one. We know it makes sense. 2790 newtons. It's hard to say if that makes sense or not, but it certainly makes sense with the scope of the numbers we're using, so we'll check mark that one too. Okay. Yep, I'm going to pause, stop the tape here, and you can keep watching the next video, but we'll stop for now.